Hello everyone, my name is Seher Fatima and today I'll be talking about my ECE 591 project for the course of Deep Learning at the University of Maine. The title of my project is BEIT V2 Transformer, Self-Supervised Learning Representing Biomedical Images. To be very precise, cancer images. The evolution of network architectures in natural language processing has taken a different path, where the prevalent architecture today is the transformer. Transformer is a deep learning model with state of art performance in vision tasks. It is highly efficient and has very good accuracy. The transformer model that we will be using today is the BEIT V2 transformer. So let's start by understanding what basically BEIT is. BEIT is a self-supervised vision representation model and it stands for bidirectional encoder representation for image transformers. For the purpose of training the model, BEIT uses MIM, which stands for Masked Image Modeling, as an objective function for training for performing pre-training tasks. Here, the MIM teaches BEIT to understand the relationship between words, where some images are masked randomly to be replaced by learnable images. The BEIT model is trained in a self-supervised manner on large images and then fine-tuned to do either image classification or image segmentation depending upon the task required. The concept of vector quantized knowledge distillation algorithm is used over here. It is used in order to better the visual tokenizer training, where the image patches are encoded using a VIT-based tokenizer. This VIT-based tokenizer allows the semantic information from a clip model to be encoded into image tokens. We'll talk about vector quantized knowledge distillation more as we proceed through the slides. A patch aggregation strategy is also introduced in the MIM. This patch, uh, this patch aggregation strategy basically helps in resolving the issue of patch reconstruction that was obtained in MIM. The data set that we are using over here for this project is the breast cancer images because the behavior of transformers in medical image analysis has not been studied much. Whether it is biomedical images or any cancer images, skin cancer, blood cancer, anything, but this thing has not been studied much. If I had to list down the three main goals of this project, then the first goal would be to train the visual tokenizer using the vector quantized knowledge destination method. The model that I'm using as a teacher over here is the clip for training the encoder and the decoder. The next part would be to, to pre-train BEIT transformer using the MIM technique. And a patch aggregation strategy which would help improving the performance of my learned representative. Finally, the last step would be fine-tuning the pre-trained weight by appending a task layer on it. And this task layer can be image classification, semantic segmentation, etc. Now, before we move forward, it is very important for us to understand the dataset that is being used over here. As mentioned, the dataset that is used in this project is the breast cancer images. The thought behind using this dataset was the increasing rate of this cancer found in women. In fact, in the United States, it's the second most common cancer. For generating the data, my colleague Jeremy Jabari, a PhD student in computer engineering at the University of Maine, had created the patch dataset for this project. The tissue slides were available online. The slides were basically split with 80% for training and 20% for validation. The patches were not split, the slides were split. And why was this done? This was basically done in order to prevent any leakage of information from the training set to the validation set. The patch aggregation here is actually beyond the scope of this paper, but at a very high level, I could just conclude by saying that it includes randomly sampling center coordinates from each slide, checking the amount of tissue that is in a proposed patch, and checking the amount of overlap with previous patches. Also, sampling along different tumor boundary types. So, getting back, the total number of images for the cancer dataset were 20,547. For training, there were around 16,137, out of which 6,037 images were cancer and 9,399 were normal images. Again, for validation, there were 4,410 images, out of which 1,981 were cancer and 2,429 were normal. The resolution of each of this image was 224 cross 224, where again each token was 16 cross 16. These are some of the images that I've attached in this presentation. If you see, this is the normal data image. This has the tumor. This has a tumor boundary. So this is the boundary and this is the tumor inside. And this is tumor and normal. And I'm really sorry, I can't really detect which part is normal and which part is tumor. That's the reason why we used a self-supervised learning BEIT model to help us understand better. Moving forward, we have the VQKD training. Well, so the vision transformers are basically the backbone to obtain image representations. Each image over here is 224 cross 224, which is split into 16 cross 16 token size. The concept of vector quantized knowledge distillation is introduced to train the visual tokenizer. The tokenizer here consists of a BEIT transformer encoder and a quantizer. The work of the quantizer is to encode the input images into vectors, and these vectors are now looked up into the nearest neighbor in the codebook, which generates a sequence of visual tokens, also known as discrete tokens. And this process is done for each patch representative. The output of the decoder aims at reconstructing the semantic features of a teacher model. The teacher model, as mentioned here, is the CLIP model. With respect to the teacher model, the encoder and the decoder are trained in order to match features. VQKD aims at reconstructing the clip feature vector and not the actual image. The other thing that it aims is to reduce the loss between the input image and the reconstruction loss by the teacher. Next comes pre-training BEIT. Like mentioned, a masked image modeling strategy is used in BEIT where some percentage of images are masked randomly and then the vision tokens are predicted with respect to these masked images. As you can see, these are the masked images and then the visual tokens over here, they are generated using this mask technique. The images are masked to about 40% for the dataset, and this is done completely randomly, and this is known as blockwise masking. A CLS token is obtained in the patch aggregation, and this token is a learnable token which is obtained by the last layer, and a patch token is taken from anywhere in between of the outputs of the VIT blocks. This CLS token is pre-trained for global image representation in order to gather information of what an image would have looked like. Like, for example, the masked image over here is a bird. So this CLS token will make sure that it has the highest proximity of the image being the bird. The visual tokens obtained by the tokenizer are then trained and the loss is calculated between the patch between the MIM head and the patch aggregation MIM head. And this patch aggregation method is only used for pre-training BEIT. Last, we have the fine tuning of pre-trained BEIT. So basically, fine tuning is performed on pre-trained BEIT by appending tasks layers on the BEIT encoder. So if this is the BEIT encoder, then task layers are appended. Mm, if you must have recalled by now that this BEIT is pre-trained with the cancer dataset that we will be feeding into it, and these are randomly initialized. There are many task layers that you can perform, such as image classification, semantic segmentation, or object detection. But for now, I went ahead with image classification due to time constraint. So here are some of my results. So the first step was training the VQKD. And on training the VQKD, I had obtained a loss of 0.15. Okay, let's talk in brief. The teacher model that I used over here was the CLIP model, and the dataset was trained for this VQKD teacher for 100 epochs. The learning rate was set to what? The learning rate was set to 1 e to the power minus 5, and it ended up taking a moderate amount of time for 100 epochs. So, if I be very accurate with you, it ended up taking almost 1 hour for me, and this is pretty good, by the way. And this was because I really had a powerful GPU. This powerful GPU kind of became contrary when I was pre-training my BEIT. It just had an adverse effect, I felt, but we'll talk about that. And the patch size that I used over here was 128. There were 12 encoder layers, three decoder layers, and about 95% of the codebook was used in training the VQKD teacher model. As you can see, the reconstruction loss value kept on decreasing with respect to the increase in number of epochs, and in the end it landed up to 0.15. Here are some of the hyperparameters um, that you can refer to. Next comes the pre-training of BEIT. Oh, this was quite a task for me. The model that I used over here was BEIT V2 base model. As we have understood by now that some of the images were obviously first masked using the MIM method, and this data set was actually pre-trained for 1600 epochs. It really took quite a time. The reason behind pre-training a model is it to better learn in a self-supervised fashion for the annotated data. The batch size that I used over here was 128. Well, to the factor, I kind of tried increasing the batch size, but that didn't really decrease my loss, so I just stuck with one. I just kept it 128. A 12-layer transformer is used with 768 hidden size and 12 attention heads. The intermediate size of feed forward network is 3072. And again, each image had a resolution of 224 cross 224, where each token was 16 cross 16. Then comes the learning value. The learning value was originally set to 1.5, but my model just didn't work with the learning rate. I kept on decreasing it until it finally ran for a learning rate of 0.7. I was really happy when it ran, but it wasn't for long because I had to train my model for approximately 2.5 days. And as I mentioned earlier, I really had a powerful GPU, but I still don't understand if 2.5 days was less or more. But yeah, it took me 2.5 days to pre-train my BEIT. Um, then the loss value ended up being 8.16, which I think was pretty great. But more than training, I had a lot of errors and issues when it came in a pre-training BEIT, and pre-training BEIT has taken the most amount of time in my project, and other than understanding the BEIT V2 model itself. So the last part was fine-tuning pre-trained BEIT on cancer dataset. Um, so basically, a task layer was appended upon the transformer, which was the image classification, and it had some parameters. So the testing image was divided into two classes, that was normal and cancer. The fine tuning accuracy was about 95.5 approximately, and it was it was fine tuned for about 30 epochs. So I think the result was pretty good. Uh, Moving forward, the data set that I used over here, as mentioned, was the cancer data set. So that was one big uh, topic for doing this whole project, to understand the behavior of the cancer data set with respect to BEIT V2 transformer, to understand if it had a better accuracy or a lower accuracy, or how could it help in future enhancement development with respect to BEIT V2 transformer. The code that I used for training VQKD, pre-training BEIT, and fine-tuning a pre-trained BEIT was available on GitHub online. A few changes were made by me here and there for as my data set was different. The data set that they used for image classification was done on ImageNet, and whereas I was doing it on cancer data set, so there were many changes done, but not something very major. Uh, yeah, so these are some of the references. Uh, if anyone's interested, this is the BEIT V2 on which my whole project was based. And to understand BEIT V2, you need to first understand BEIT 1. So I think this and then this would be a better approach. You can even do this. So I think these three would be a good approach. So I would like to conclude by saying that I'm kind of satisfied with what I have achieved, but moreover, I am more happy about the fact that I took up this challenge as the paper was just published in October 2022. And within a month, I was able to come with some kind of result, not the best result, but some kind of result. And I'm more than happy that I had the opportunity to work on a state of art topic. And in fact, it was my first time working on a state of art topic. Well, all thanks to my ECE 591 deep learning course. Thank you.